systems of particles, and basically if individual particles are acted on by a force the center of mass of the system will accelerate in the direction of the net force. So if I have a mass here and a mass here, we'll say that they're the same mass and they are stationary, we know that the center of mass of those two objects is in between them. Well, if we exert a force F on this object and then an equal and opposite force F on that object, the net force in that entire system is zero. So there should be zero acceleration of the center of mass. This particle will accelerate away. This particle will accelerate away. However, that point will remain stationary. If I had a different system where one mass is there, another mass here, force exerted on this mass, center of mass starts in the middle, but if we do not apply a force to this, as this mass accelerates this way, the center of mass would then accelerate in that same direction. And I think we can assume that if this is A, the center of mass acceleration is going to be half of A, since the acceleration is going to depend on the total mass. So the net force is equal to the total mass times the acceleration of the center of mass. If we rearrange that for the center of mass equation, we will get the net force over the total mass, which is just another way of summing up the different quantities, similar to finding the center of mass. And we get a similar equation. Okay? And we can do this if the forces are in one direction, 2 dimensions. And I don't think we'll do 3 dimensions, but it is also possible to do it there. So you could have 3 particles in space. If that was where can we put the center of mass would be shifted towards there. If there's a force this way, a force this way, and a force this way, you know, all 3 of these particles will accelerate based upon the vector addition of all those forces. This would then accelerate in the direction of the net force. All right? And that's the same way that we would add 3 forces acting at the same point. And if we take that same equation and we wanted to figure out how the velocity is affected, this is dv dt. This is the differential equation. And if we rearrange this, so I'm going to bring the mass over, so I have dV times the total mass. Here I have the net force, dt, if we integrate both sides, this side with respect to v, this side with respect to t, well, this just becomes m times v, and it would actually be the center of mass, because dv turns into v. Well, the integral of force times time is momentum, and it's the net momentum since it's a net force. So just like in this equation, the velocity of the center of mass would be equal to the net momentum divided by the net mass. Why that's important. There are conceptual questions in the multiple choice that I've seen that if you use the idea of the center of mass in momentum, it makes it a lot easier. This thing keeps getting out of focus. All right, so two masses, they're the same mass. At this point in time, this center of mass is in between them if they're equal. This ball is stationary, this ball is moving. At some time later, this ball has moved some distance, this ball has remained stationary, the center of mass has moved closer to the other object, and then it just keeps happening until there's contact, and then this one begins to move away, at that speed. Now, if I were to be able to draw this good, or better, we would see that this would kind of have a straight line slope there, because the center of mass, the velocity of the center of mass, will remain constant the entire time. It will be the same velocity here as it is here as it is after the collision. And basically saying that the net momentum of the system will not change, the net mass of the system will not change, so therefore the velocity of the center of mass will not change. So it doesn't matter how the collision occurs. If I have a block sliding this way at a high speed and hits a much larger block that is stationary, okay, what could happen after the collision is that the first block can be sent backwards while this block is sent this way at a very small speed. All right, so even though this one is moving towards this block, and it's just talking about the center of mass with respect to momentum, well, the total momentum moving forward here is going to have to equal the total amount of momentum moving forward here. So the center of mass will still move with the same exact speed before the collision as well as after the collision, since the momentum of the system is conserved. It can never be changed. And that value will always be constant. All right, that's it.